Hello everyone, my name's Dr. Vile and welcome back to my A-Level Chemistry YouTube channel. This channel is all about getting you ready for your A-Level Chemistry exams, and this specific video is all about a technique called mass spectrometry, which is a molecular weighing scale for measuring the atomic mass of different atoms as well as the molecular mass of compounds. And we're going to spend some time explaining how it works and what useful information we can get from it. If you find these videos helpful, remember to like, subscribe, and keep checking back for more content. So you've probably heard of a couple of occasions where mass spec has been quite famous in the news even. So back in 2012, and this happens at every Olympics, all the athletes have to give urine samples ready for a drugs analysis. And this Russian shot putter had her gold medal taken off from her because she had an illegal steroid called metanolone in her of a level that was unacceptable by the rules, and it was detected using something called a GCMS. So that's gas chromatography mass spectrometry, GCMS. And what the GCMS does is it firstly separates all of the different chemicals that are in a mixture. So you insert your sample into the GC, and then it goes through a long column where all the different chemicals are sort of flying through the column, and they all go through the column at different rates, so they all exit the column at different times. And then they get fed into the mass spectrometer, and the mass spectrometer is a detector. In other words, it detects what the chemicals are and how much of them there are as well. So in the case of the shot putter, a urine sample would have had loads of different chemicals in there. These chemicals would have been separated in the column and then passed into the mass spectrometer where they were detected and weighed in terms of their molecular mass. And we're going to look at how that works in more detail. Another famous example where you've probably heard of a mass spec is on board the Mars rover, which also has a GCMS on board, and what it is looking for is different elements that are essential to life, such as carbon, nitrogen, oxygen, sulfur, oxygen, and it's trying to detect simple organic matter, trying to prove if at any point in the past there would have been life on Mars. So mass spec is very powerful, very important, and we need to understand how it works. So let's look inside the mass spectrometer. So the diagram on your screen at the moment is courtesy of chemguide.co.uk, and it's showing us what happens inside the mass spectrometer in simplified terms. And we'll look at each of the steps one by one. So the first step is that you vaporize your sample so that it is in the gas phase. So if it was a liquid, you turn it into a gas. So for instance, here M, which is just our sample, goes to M gas by heating it. So once your sample is in the gas phase, it is ionized by firing high energy electrons at it. So here's your sample, your M in the gas phase, plus one electron, which comes from the beam of electrons. That'll give you M plus, which is your ion, and then two electrons. Now you might be wondering where the two electrons are coming from. The first electron is the electron that has been dislodged from M, and the second electron is the one that you fired at it. So it knocks off one electron and then is released itself, hence two electrons. Another way of writing this would be just simply M gas goes to M plus gas and E minus. That's the simplified version of the equation above. But anyway, at this stage you have your gas phase ions and they're ready to go. They're ready for the acceleration stage. So at this stage, the positive ions that we've created in step 2 are repelled by positive plates. So we have these sort of electrically charged plates. They're repelled by positive plates and they're accelerated towards negative plates, because remember, opposites attract. And the aim is so that all the ions have the same kinetic energy. And these ions are now moving very, very fast, and they need to go through an electromagnet, and we'll see what the purpose of that is in the next step. So at this stage, the ions are moving fast and they enter a magnetic field which is caused by the electromagnet. And they get deflected in the magnetic field according to two things: their mass, so how heavy they are, and their charge. Now the general principle is the lighter the mass, the more the deflection. If you could imagine going to kick a bowling ball and kick a football, because the football is lighter, you can deflect it more from its original course than you would a bowling ball. So lighter ions get deflected more than heavier ions, and they're also deflected according to their charge. Now, to keep things simple at A level, we typically deal with +1 ions in the mass spec, and the amount of deflection depends on the mass per charge ratio, m per z, and you'll see this on a lot of the mass spectrums. And if the charge is just simply +1, then effectively what we're saying is the amount of deflection depends on the mass. And we can kind of ignore the charge, but it has to be a positive ion, otherwise it won't go through the mass spec. And this all happens under vacuum, so we have a vacuum pump here that's pulling all of the air out of the mass spectrometer. And this is important because if there were any air molecules in there, they could collide with the ions and prevent them from getting through to the detector. So this all has to be done under vacuum. And then finally, we get to the detector, and the ions are detected electrically. So if you can picture your positive ion arriving at the detector, and at the detector, it combines with electrons, so that it becomes neutral again. And the flow of electrons towards these ions is an electrical current, which is what gets sent through to the computer, and you get your mass spectrum. So that's the kind of the principle of how the mass spectrometer works. Now we need to look at the kind of information you get from it. So here is the mass spectrum of neon. On the x-axis, you have this m/z term that we talked about earlier, which is the mass per charge. But remember, because we said the charge is +1, this is effectively just the mass. So you've got the mass of the different isotopes going along the bottom. Remember, isotopes are heavier or lighter versions of the same atom because they have different numbers of neutrons. So what we're saying here is that neon has 3 isotopes. One weighs 20, one weighs 21, and the other weighs 22. And then on the y-axis, we have the relative abundance, which tells you the relative amounts of these isotopes. So effectively what this is showing us is that if I had a jar of neon, about 91% of it roughly would be neon 20, less than 1% would be neon 21, and then 8.8% of it, or 9% roughly, would be neon 22. And what we're going to do is look at how we can use this data to calculate the relative atomic mass of neon, which is the mass that factors in the 3 different isotopes. So the equation that we need to calculate the relative atomic mass for an element is the percentage of the isomer, so percentage of isomer A, times the mass of isomer A, and then plus the percentage abundance of isotope B, times the mass of isotope B. And then we divide this by the total abundance, which should be 100, because all the percentages should add up to 100. In this equation here, I've only done it for 2 isotopes, isotope A and isotope B, but you could just keep on extending that if you had 3, 4, 5, however many different isotopes you have. But it's best looking at a real example, so let's stick with neon and do the calculation. So to do the calculation here, what you do is you take the percentage of the first isotope, which is 90.9, and you times it by 20, which is the mass of the first isotope. Then you do the same for the second one, you add it, so it'll be 0.26 times 21, and then you add that to the next one, which is 8.8 times 22, and you divide that all by 100, because it should, but then it's not exactly 100, but it's pretty much bang on 100. All the percentages should add up to 100. And then you put that into your calculator, and that comes out to 3 significant figures as 20.2. Now, when you look at your periodic table on the exam papers for A-level chemistry, you'll find most of the atomic mass numbers are to 3 significant figures, and you'll see some numbers that are not whole numbers, and that's because they are the weighted average of these isotopes, and they've just done the calculations just like this to work it out. So just to illustrate this one more time, here's an exam question which is all about lead. And it says naturally occurring lead consists of a mixture of stable isotopes 206, 207 and 208. And then you've got the percentage abundance of each isotope in this column. And your task is to calculate the relative atomic mass for this sample of lead, giving your answer to 4 significant figures. So what I would suggest you do at this stage is pause the video, have a go at the calculation, see how you get on, then unpause it, and I will go through it. So hopefully you've had a go at that. The first thing you do is take the first isotope, which is 206, and you times it by 25.48. I put these in brackets in my calculator just to avoid a calculator error. Then we're going to add that to 207, which is the second isotope, times 22.12, and then the third isotope, which is 208, times 52.4, and we're going to divide that all by 100, and to 4 significant figures, the answer comes out as 207.3. Now, when you get an answer for a calculation like this, you should be able to check, is it a sensible number? So it would make perfect sense that your answer is somewhere between 206 and 208. If you get a number that's somewhere outside of that, then something has gone drastically wrong. So you should be able to check that your answer seems vaguely sensible once you've done the calculation. Okay, so we've looked at the mass spectrum for neon, and I want us to look at a more complicated example now, the mass spectrum of chlorine. And the reason that chlorine is more complicated is that it exists in pairs. It is what we call a diatomic molecule. So chlorine exists with a covalent bond between chlorine atoms to make a chlorine molecule. And chlorine has 2 major isotopes, chlorine 35 and chlorine 37. And if you were to have a jar of chlorine, 75% would be chlorine 35 and 25% would be chlorine 37. So in other words, there's 3 times as much chlorine 35 as there is chlorine 37. So you'd expect to see 2 peaks on the mass spectrum, one at 35, one at 37, and the peak of 35 would be 3 times the height of the peak of 37. However, this is assuming we have chlorine atoms. Remember, we have chlorine molecules, so the picture is actually a bit more complicated than that. So when you combine 2 chlorines together, you could have a 35 with a 35, which would give you 70. You could have a 35 and a 37, that would give you 72, or you can have a 37 and a 37 that give you 74. And actually then what we see is three peaks, one at 70, one at 72, and one at 74, and they come in the ratio of 9 to 6 to 1. So you need to know that there's that ratio of the chlorines, but we need to be able to explain it as well. So if you remember, we said that 3/4 of all the chlorine in the world exists in chlorine 35. So the probability of combining two chlorine 35s together is 3/4 times 3/4, which is 9/16. You'll see where I'm going with this in a minute, hopefully. So that's that one there. And then the odds of combining a 35 and a 37 would be 3/4 times 1/4, which is 1/16. Sorry, I'm being stupid there. That's 3/16. But you could also have a 37 and a 35. They would both give you the peak at 72. So technically that could be 1/4 times 3/4. So that's 3/16. And because both of these would give you the peak at 72, you add them together, which gives you 6/16. Hopefully you can see the 9 to 6 part of our 9 to 6 to 1 ratio. And then lastly, the 1. Well, that's a 37 and a 37, so that's 1/4 times 1/4, which is 1/16, hence the 9 to 6 to 1 ratio. So that's why you'd expect to see three peaks, 70, 72, and 74 in that 9 to 6 to 1 ratio. However, that's not the full story, because the chlorine molecules, due to the high energy of the mass spec, they fragment, which means break apart, to give chlorine ions, this Cl+. So what you actually find on the mass spectrum is you find 5 peaks. You have a peak at 70, 72, and 74, like we've just discussed, in this 9 to 6 to 1 ratio. But then also you have 2 more peaks at 35 and 37, and these are in a 3 to 1 ratio. And there's no link between these peaks here and these peaks here in terms of the heights, because it depends on the amount of fragmentation. So that's what the mass spectrum for chlorine would look like. So when we think of fragmentation, this can be very useful for determining the structure of organic molecules. So if you put an organic molecule into the mass spec, the most obvious thing that you get is something called the molecular ion, and that will basically give you the molecular mass of the compound, which is where there's been no fragmentation, just ionization, and that will give you the molecular mass of the compound. But then this molecular ion can fall apart into different fragments, and that can help us to identify the structure of the organic molecule. So if you take something like pentane, now pentane has the formula C5H12. That would give you a molecular ion at 72. So this peak at 72 corresponds to all of this structure here with a positive charge. And that would give you your peak at 72. If we were interested in the peak at 57, notice that that's a loss of 15 from the 72. So 72 minus 15 gives you 57. So we have to lose something from this structure up here that weighs 15, which happens to be a CH3 group. So the peak at 57 would be CH3, CH2, CH2, CH2. You put that in square brackets and a positive charge at the top, and that's your peak at 57. The next peak down is a peak at 43, so that's a loss of 14 from this structure here. So we're interested in this one here now. So that's going to be this one here minus a CH2 group. Put it in square brackets. And that's your peak at 43. And then lastly, the peak at 29. That's the loss of 14 again. So that's the loss of a CH2 group. So that's CH3, CH2. And that's with a positive charge. Okay, so when you get an organic molecule like this, you should be able to identify the fragments. They're always positively charged, otherwise they won't go through the mass spec. And basically think of this as having a little pair of molecular scissors, and you're able to chop your molecule up into smaller sections, and they're called fragments. So we're going to look at a couple more examples and then we're finished. So this one here is the mass spectrum of pentanthreone. So pentanthreone, it has the structure CH3, CH2, CO, CH2, CH3. I'm not going to go into the structure of ketones too much in this. It's simply enough to know the structure. We can look at that in another video. But if you have all of this and you work out its molecular mass, this will correspond to the peak at 86. Whereas the peak at 57, that's a loss of 29. So that must be the loss of the CH2, CH3 group. So that would be CH3, CH2, CO, square brackets, positively charged. And that corresponds to this peak here at 57. And then lastly, the peak at 29, that must be CH3, CH2. And that's your peak at 29. Okay, so lastly, we've got the mass spectrum of ethanol. Now, hopefully you can see that there are 5 peaks here, 46, which corresponds to this one. The peak at 45, that corresponds to this one here. And then 31. And then 29. And then lastly, the one at 15, which is this one here. And we need to be able to identify what all of them are. So the peak at 46 corresponds to the molecular ion, the structure of ethanol. Now ethanol is CH3, CH2, OH. So that's the whole thing there. And therefore the peak at 45 must be the loss of a hydrogen, which will be the hydrogen from the OH group. So that's CH3, CH2, O. Now the peak of 31, this one here, the peak of 31 is the loss of 15 from the original, which actually must correspond to the loss of a CH3 group. So that would be the CH2, OH. The peak at 29 would be the loss of the OH group, which weighs 17. So that would be CH3, CH2. And then the peak of 15 must just simply be CH3. And these are all positively charged. Okay, so I hope that's been helpful going through the mass spec. In this video, we've learnt what a mass spec is, how it works, what information we can get from a mass spec in terms of determining the atomic mass, but also we've looked at the molecular mass for compounds as well as fragmentation patterns. And you'll need this information for WJC. You need it in Unit 1, where you're looking at how the mass spectrum works for calculating atomic mass. You'll need it in Unit 2 for the organic molecules, and again in Unit 4 as well. So it comes up in a lot of different places, and possibly in Unit 5 as well with the spectroscopy. So very, very useful technique, and I hope this video has been helpful. So thank you for taking the time to watch it, and I will see you next time. Bye everyone.